Okay, so welcome to this video. This video we're focusing on our CCENT ICND1, specifically Chapter 6, Building Ethernet LANs with Switches. This is coming out of the Odom 2013 Cisco CCENT CCNA ICND1 for exam 100-101. This does have the network simulator attached to it, but for these videos, we're not focusing on the network simulator. Alright, so the objectives so far are LAN switching concepts and design choices in our Ethernet LAN. So, first thing is we have to talk about some history. Here's a hub. A hub is basically a multi-port repeater. If you have one input, let's say Larry, it will clone that signal and send it out every other port that it was not received on. So you'll actually send it to both Archie and Bob because, again, they're connected. It will not go back to Larry because that's the receiving port. We don't really deal with hubs anymore, but they're still out there, so we have to talk about them. Then we have bridges. Bridges create two collision domains and two shared Ethernet networks. A collision domain is essentially the domain where we deal with our collisions, two devices talking to one another. Normally, if you have a hub, you have one giant collision domain, meaning everyone is going to fight with everyone to communicate. A bridge is a dumber device that allows you to connect two separate collision domains. A switch, however, is a smart hub. Every individual port is its own collision domain. So any port that's connected to any device is its own separate collision domain. And it learns. It knows what MAC address goes to what interface. It knows how to forward frames based off of the interface and based off of the MAC address. For a sample switch forwarding and filtering decision, we can look at this. If the frame came in F or Fast Ethernet 0/1 is destined for a specific MAC address, it could look up the MAC address and then it will know to send it out the appropriate interface. Meaning it knows that destination, so it doesn't have to broadcast to Wilma or Betty because it already knows Barney's PC name is that MAC address. Not so much its name, but it knows it's the name of the PC is associated with that MAC address, which is associated with that interface. Forwarding decisions with two switches. Same similar concept. Fred will send out to a destination. If it doesn't know where it is, for example, we now want to go to 020033333333, and we know that's Wilma, our switch 1 will actually have on its gigabit interface the MAC addresses for switch 2. That way it will know that if it receives the MAC address that resides on switch 2 to forward out that interface, that way switch 2 can get it, and switch 2 will then filter it to the appropriate interface. So switches learn by powering on. They'll have an empty table, and as basic communication happens, they will start adding to their address table, both frames and IPs. With IPs, it's subjective because we're going to have a layer 3 device for that. But I mean, they start learning their address table, so that's the important part. We have the ability to take out things such as STP or spanning tree protocol, and that is if we have a switching loop, we have the ability to prevent that loop by turning off specific interfaces. That way, a loop doesn't occur. Switching internal processes, we have big three. Realistically, we have big two. Store and forward and cut through. Fragment free is not really one of the main ones, but fragment free, the switch forwards the frame after receiving just the first 64 bytes of the frame, thereby avoiding forwarding frames that errors could happen. So cut through. The switch will start forwarding the frame as soon as it can. So as soon as it has the destination address, it will start forwarding, meaning it reduces latency. But if the frame is damaged, it doesn't actually do the error checking for that frame. Store and forward will wait to receive the entire frame, will verify there is no errors, then forward it. But it's a slightly slower process. Collision domains. Here we have separate devices. So how many collision domains do we have? We have, I'm going to get my pin out. Each one of these PCs is its own collision domain. That guy's an interface, so that's its own collision domain. So far that's 3. Here we have 4. And this is a hub, so we have 5 collision domains. I know it says 5 collision domains, but why? So I wanted to point that out. Broadcast domains are domains that separate broadcasts at layer 3. Now, broadcast is going to be a message sent to everyone trying to get a specific type of information. Routers do not forward broadcasts. So here we have 2 broadcast domains. One on this side, one on this side. So we have 2 broadcast domains and 5 collision domains. Benefits, greater cable distances, all of them for hubs, switches, and routers. Creates multiple collision domains. Hubs are no, but switches yes, routers yes. Increased bandwidth. Hubs no, because again, they are just a multi-port repeater. Switches do increase bandwidth, so do routers. That's because here, each individual link is separate from one another. Creates multiple broadcast domains. That's only a layer 3 device, so that could be a router, or possibly a layer 3 switch. VLANs. So I'm assuming that you guys had a basic networking course. So we've already talked about what VLANs are. So just in case you haven't, double check my CCENT videos for VLANs. So a sample network with 2 broadcast domains and no VLANs. These are all separate networks. We could actually do this entire thing with one switch, with this being part of one VLAN and this being part of a second VLAN. Still separate broadcast domains because they're separate networks, but they're virtual networks. Next, we have a campus LAN with specific design terminology. So I have some problems with this because I do have a CCDP, and this two-structure model doesn't work for me. Realistically, we would be adding a 3rd layer up here for our core. So normally for a switched environment, we have 3 layers: access layer, distribution layer, and we have a core layer. The data center and all high-speed backbones are happening at the core. So if we use a campus for an example, each floor could have an access layer switch. Maybe each room had an access layer switch. And then every room on each floor will connect to a distribution switch. So there will be one main distribution switch per building. Each building connects to the campus core. That's a general design that's pretty popular. We have our different types of media: 10 base T, 100 base T, 1000 base T, and then our different types of fiber. With 100 base T and above, we're normally using Cat5, Cat5e, maybe Cat6 or 7. Anything that doesn't have a T should be a fiber, multi-mode or single mode fiber. It's pretty popular. Auto negotiate. So our port will negotiate with our nodes. So if we have a 10100 NIC, even if we have a gigabit port, it will negotiate to the slowest speed. So here our slowest speed is 10, so we should get 10 megabits. What's this full? Well, that's duplex. Can we send and receive at the same time? So, normally with that auto negotiate, it will try to do duplex as well. Is it send and receive or just send or receive? If it says full, that means send and receive. But you'll notice if one side's full, one side's half, it will then go to just half. If one side's half and the other side's half, it goes to half. It has to be set to full duplex on both sides for them to actually communicate in full duplex. Negotiating with a hub. Hub will actually auto-negotiate down to half duplex, while the switch will negotiate to full duplex. So on this side, this will be full. On this side, it will be half. And that's actually all I had for this video. Again, if some of what we talked about doesn't seem familiar, double check the rest of my videos for my CCENT1, my CCENT2, because that outlines all of the material that you need to get caught up. Thank you.